In this lesson, I will explain the inverse trigonometric functions, that is sine inverse, cos inverse, tan inverse, etc. It is expected that you have a basic familiarity with the trigonometric functions sine, cos, tan, sec, cosec and cot. I will discuss how we restrict the values of inverse trigonometric functions to make it a one-to-one function, and then I will go on to work out the graph of x versus sine inverse x function. A trigonometric function, for example sine, takes an angle as input and gives the ratio sine of that angle. This small c here denotes that the angle is in radians. So sine of 0 radians is equal to 0. Sine of pi by 6 radians is equal to 1 by 2. Sine of pi by 4 radians is equal to 1 by root 2. A corresponding inverse trigonometric function does just the reverse. It takes the ratio sine, this ratio, this number, as input and gives the angle whose sine it is. The mathematical symbol for angle whose sine is y is sine inverse y, written as sine with a minus 1 in the superscript y, pronounced as sine inverse y. So corresponding to each of these statements, I can write sine inverse of this 0. Sine inverse of this 0 is this 0 radian. Sine inverse of this 1 by 2 is pi by 6 radians. Sine inverse of this 1 by root 2 is pi by 4 radians. Keep in mind that while the symbol sine square y is used to mean sine y into sine y, or you can say sine y whole square, a very similar looking symbol sine inverse y is used for an entirely different purpose: the angle whose sine is y. Simple, isn't it? Wish all things in life were as simple. Unfortunately, they are not. All trigonometric functions are many to one functions, which means sine of multiple different angles works out to be the same value. Sine of pi by 4 is 1 by root 2. Sine of 3 pi by 4 also works out to be same 1 by root 2. Not only this, you add another 2 pi. It will again work out to same 1 by root 2 and so on. This angle is not shown on this graph. This graph ends here at 2 pi, but after this, the same curve repeats on again and again. So sine pi by 4 and you add another 2 pi to this, it will go beyond this, or you subtract from pi by 4, you subtract 2 pi, you will reach somewhere beyond this side. Since the curve is repetitive, sine of multiple angles, you keep adding 2 pi, 4 pi, 6 pi, you will keep getting the same result for sine 2 pi plus pi by 4, sine 4 pi plus pi by 4, they will all work out to 1 by root 2. Select a value of x, say pi by 4. Draw a vertical line from this point. The line has to extend indefinitely to positive and negative directions of y. Find the intersection with the graph. Draw a horizontal line from this intersection till you reach y-axis and you get 1 by root 2. As you can see, this vertical line intersects the graph at exactly one point. Exactly means no more than 1 and no less than 1, which means for any given value of x, there is exactly one value of sin x. Since the graph extends indefinitely to negative and positive side of x, sin x is defined for all values of x from minus infinity to plus infinity. Also, notice the value of sin x is always between minus 1 and plus 1. Nowhere does it go below minus 1 and nowhere does it go above plus 1. This square bracket here indicates minus 1 is included in the possible values of sin x, plus 1 is included in the possible values of sin x. This small bracket here means minus infinity and plus infinity. Since infinity is not an actual number, value of x cannot be minus infinity. However, it can be as small, as big a negative number as you want, or as big a positive number as you want, excluding infinity. That is why this is small bracket. Using the same graph, let us try the reverse. That is, find the angle whose sine is 1 by root 2, which is same as saying find sine inverse 1 by root 2. This time, since the value of sine of some angle is given as 1 by root 2 and we need to find the angle, so we start from the y-axis. Find 1 by root 2 on y-axis, that is here, and draw a horizontal line from that point. The line has to extend indefinitely to positive and negative directions of x. The line intersects the graph at multiple points. It intersects here, here, and since the graph is repetitive, it will intersect the graph many more times, infinitely many more times, as the graph keeps extending to both sides. In this case of finding sine inverse of 1 by root 2, this line cuts the graph at multiple points. So sine inverse 1 by root 2 has multiple values: pi by 4, 3 pi by 4, then again somewhere here, then this side, and so on, which can range from minus infinity to plus infinity. Rather, I would say the general value of sine inverse 1 by root 2 has multiple values. Shortly, I will discuss how we restrict the definition of sine inverse so that it gives only one value. Sine inverse, or rather sine inverse y, is only defined for y in the interval minus 1 to plus 1. This value of sine x I cannot begin with, value of y I cannot begin with anything beyond plus 1 or below minus 1. Then the graph does not exist in that range and there is no angle whose sine gives me a result of greater than plus 1 or less than minus 1. For example, sine inverse 3 by 2 is not defined. One of the preconditions of a function is it should not give more than one result for any given value of its variable. For any one value of x, the value of fx should be only 1, not more than 1. The sine inverse in its general form, as we discussed here, does not follow this condition. It results in multiple values. The sin x graph can be split into many sections, as shown here, such that any one of these sections can be used to find angle whose sine is given to be y. If I have the value of sine y which is anywhere in the range of minus 1 to plus 1 and I want to find the angle one section of this graph is sufficient to give me an angle for any given value of sin x in this range. I can use either this section or I can use this section, or the graph extends further, so this section or this section. So there are multiple such sections, and any one of these sections can be used to find an angle whose sign is given to be y. So once y is given, I can find sin inverse y using any of these sections. In general, each of these sections will yield one value of sin inverse y for a given value of y. We have named one set of values of sin inverse y arrived at using one of these sections, this section marked here in red, as the principal value range. Though it may be rather arbitrary, or it may sound to be rather arbitrary, but we have selected this one section and called it principal value range of sin inverse y. So the principal values of sin inverse y will always be in the interval minus pi by 2 to plus pi by 2, both endpoints included. For y is equal to minus 1, sin inverse y is minus pi by 2. For y is equal to plus 1, sin inverse plus 1 is plus pi by 2. So both endpoints included, the principal values of sin inverse y will always be in the interval of minus pi by 2 to plus pi by 2 and nowhere outside this. Just to repeat, we could say, while the general values of sin inverse y or sin inverse 1 by root 2 results in multiple different angles, there is only one principal value for a given value of y, which can be found out using this red marked section of the sin x graph. Going further, it is an accepted convention for all mathematical communications that the symbol sin inverse y by default always means principal value of sin inverse y. For all other values, one needs to specifically mention alternate values of sin inverse y. Whenever you see sin inverse y or sin inverse x in your book or in exam question papers, be aware that it means the principal value of sin inverse y. To summarize and to repeat, if I am given the angle x and I have to find the value of sin y, I will use this graph, find the value of x on this axis, draw a vertical line, go to the horizontal side, find the value of y, and this graph extends minus infinity to plus infinity. So value of x can be anything from minus infinity to plus infinity, and I can use this graph to find sine of any given angle. I can use the same graph in the reverse direction. Once value of y has been given, I can locate y in this axis, on the y axis. But notice here, I can only find value of y for which an angle exists in the range of plus 1 to minus 1. So for finding sine inverse y, I will locate y on this axis, draw a horizontal line, and then since I am interested only in the principal value, I will have to take only this section of the graph. When we talk of value of y is given and I have to find sine inverse y, it's a convention to use the letter x for the variable which is given and use the letter y for the value which has to be found out. It's a convention. Whether I say y here and sine inverse y or x here and sine inverse x, basically it means the same thing, but it is a convention that the given variable is named x and the calculated function is named y, and when a graph is drawn, the given variable is drawn on the x-axis. So while in this case I have been using the same graph to find sine inverse by locating the given value on the y-axis and then arriving at the corresponding value of x, and I am using the same graph to find sine of an angle by locating the angle on the horizontal axis and arriving at the sine of that on the vertical side. But as a convention, if I have to draw a graph of sine inverse of an angle, I will call angle as x, and the sine inverse x I'll call that as y, and I will put this on the y axis. So the same graph, only this red section will now look like this. For value of x as 1, sine inverse x is pi by 2, which means sine of pi by 2 is 1. For value of x is equal to minus 1, sine inverse minus 1 is minus pi by 2, which means sine of minus pi by 2 is minus 1, and anywhere in this range. The graph ends here because value of x cannot go beyond plus 1 and minus 1, and correspondingly the value of sine inverse x, since we have restricted ourselves to only principal value range, the sine inverse x will always range between plus pi by 2 and minus pi by 2.